All right. So let's actually do that analysis in a little bit general. So let's say on the left, W is equal to WL, and on the right, W equal to, well, let me do the analysis in green, and WR. So left value, right value. And let's actually just use a more general flux function. Let's just down to restrict ourselves to Burger's equation. Plus FWB minus FWA. Let's actually make this equal to minus this plus this. All right. Okay. In general, before we do further analysis, let's just say a little bit about what is the meaning of that equation. Why is it called a conservative form, right? So, and why is F called flux? Here, W can be used to represent some kind of the density of some kind of conserved quantity. So, for example, if W is the density, like the regular mass density, okay, then the integral over interval of the mass density is what? Oh, it's mass, right? So the integral of density is always the conserved quantity, right? So if it's mass density, then the integral is mass. And if the derivative of mass within the interval is equal to what? I mean, if it's conserved quantity, if mass is conserved, then what is the derivative of mass over a fixed spatial domain? It's what? Is mass what? Sorry? It's flow. It's flow, yes. So if nothing goes in and out of the domain, the derivative of mass should be 0, right? So the derivative of mass would only be non-zero if something is moving in or something is moving out. If something is moving in, it'll cause the mass to increase. If something is moving out, it should cause the mass to decrease. And if you look at this, this is exactly the rate of mass moving in from the left. This is exactly the rate of mass moving out from the right. Okay, that's why it's called the flux. Flux is, well, in one dimension, flux, in one spatial dimension, flux is the rate of conserved quantity moving across a spatial point. That's what flux is. In 3 dimensions, we also have similar fluxes. The flux would be the rate of conserved quantity moving across a certain point in a particular direction per unit area. It's a little bit more complex in 3D. You have to. So in 3 dimensions, here you would have a volume integral, and instead of just writing down the flux, you have to integrate the flux over the surface encompassing the volume. We'll do that analysis let's see, next lecture to make things a bit clearer. Okay, so here let's start analyzing how the shock wave is going to behave. All right. So if my let's actually look at use the over here WL, WR, and so let's choose a point A, right? So this is let's write it here. So this is X, this is W, this is A, this is B, and integration over A and B of total W, which is the area underneath the curve. Its time derivative is equal to FWB minus FWA. So that's what we just derived on the integral form, right? Wait, no. Opposite. So A is moving in from the left and B is moving out from the right. Okay, so that's my flux. Okay. Right. So first of all, if I have a flat region on left and right, I mean, if I zoom into the shockwave enough, right, the left and right of the shockwave is going to be looking like flat anyway, right? Okay, so now if that's the case, according to the behavior of the smooth region, I mean, if you just look at the differential equation, right, the smooth region is you have dw dt plus my uw dw dx equal to 0. So on the left and right, dw dx is approximately 0, so dw dt is also going to be approximately 0, right? Okay, so that means even if it's not 0, the movement up and down should be very small in a very small time. So now the flux is like this. So what is going to be the dominant mechanism for the total area to change? I'll give you 3 possibilities. One is that WL is going to move up and down. So imagine it moves down a little bit. It becomes like here in the next moment. Okay. Second mechanism is WR may move up and down. So let's imagine WR move down a little bit. Third mechanism is the location of the shock wave is going to change. Let's imagine it moves right a little bit. Which mechanism is going to contribute to ddt of the integral between a and b the most, assuming I'm taking a very, very infinitesimal interval around the shock wave? Motion of the shock. Why? That's right. So if I am truly taking a very infinitesimal interval, then the movement of WR and WL is going to cause an area change proportional at most to be the rate of change of WL or WR times the size of the interval, right? And if the size of the interval is small, that contribution is going to be small compared to the movement of the shock multiplied by the magnitude of the shock, right? The magnitude of the shock is fixed. It doesn't depend on if I shrink the region A and B, right? If I shrink the region A and B, the first contribution and the second contribution go smaller and smaller and smaller. But the contribution from the movement of the shock is not going to go any smaller. So let's just think we are taking truly infinitesimal interval and B, and just imagine the complete contribution is from the movement of the shock. Okay, so if all the contributions are the movement of the shock, then the increase in the area is just the WL minus WR times what? Times the speed of the shock. Let's just write U shock, right? If the shock is moving towards the right at the rate of U shock, then basically I'm counting this area. This area is U shock times delta t, right? If the shock has moved over a spatial distance, U shock times delta t. That's that multiplied by the difference between W and WR is the increment in the area. So the rate of increment in the area is just the U shock times WL minus WR. Agreed? Okay, that's actually equal to F W A, which is WL, right, minus F of WR. Hereby, we just derived the speed of the shock, right? The speed of the shock has to be, well, I'll just write a delta of F over delta of W. Right, so this is the difference between the flux on the left and right of the shock. Well, this is the difference between the solution, the conserved quantity between left and right of the shock. So the speed of the shock is simply the delta flux over delta solution.